The previous video ended with the question, how can induction be confined within the limits of common sense? And the suggestion that perhaps Bayesian inference is a way to do that. Understanding the suggestion, of course, requires knowing what Bayesian inference is. So let's start. Imagine we have a doctor here, a medical doctor, and a patient. And the medical doctor asks the patient if she can test him for a virus. And the patient says, look, I feel fine. Why would you test me for a virus? And the doctor says, I'm just testing people randomly. And the patient agrees. So the doctor goes and draws some blood and then goes off and comes back and says, hey, you tested positive. And the person's like, wait, what? I don't feel sick at all. And the patient asks, well, how accurate is your test anyway? And the doctor says, it's 90% accurate. And the patient says, so there's a 90% chance I'm infected? And the doctor says, sadly, but luckily a statistician comes and interrupts and says, hold on, how prevalent is this virus? And the doctor says, what do you mean? And the statistician says, what percent of people in the population as a whole have the virus? And the doctor says, it's 1%. And the statistician does some quick calculations and says, then there's an 8% chance you're infected. And the doctor and the patient both say, what? If the test is 90% accurate and I tested positive, how can there be only an 8% chance that I'm infected? And the statistician says, let me explain. Suppose 1,000 people are selected at random to be tested. And suppose that only 1% of them are infected. So that's the prevalence in that population. And let's just suppose that's a random sample and it's reflective of the population. So 1% of people in the general population have the virus. We're just looking at 1,000 of them. Well, of those 1,000, how many are actually infected? 1% is 10. So only 10 of those 1,000 are infected. And of those 1,000, how many aren't infected? Well, 990 of them aren't infected because 1% of them are infected, which means 99% of them aren't infected, and 99% of 1,000 is 990. Now, we know the test is 90% accurate. So how many of the 10 over here who are infected are going to test positive? Well, 9 out of the 10, since the test is 90% accurate, so 9 will test positive. And again, we know the test is 90% accurate, which means it's 10% inaccurate. So how many of these 990 who aren't infected is it going to get wrong? It's going to get 10% of them wrong and say they are, in fact, infected. And 10% of 990 is 99. So you're going to get 99 positive tests from those who aren't infected and 9 positive tests from those who are infected. So you'll get a total of 108 positive tests. Now, how many of those 108 are actually infected? Well, 9 of them. So 9 of the 108 are infected. So 9 out of 108 people who test positive are actually infected. And 9 out of 108 is 8%. So 8% of people who test positive on this test, which is 90% accurate, are infected. And what's crucial to see, what I really want you to sort of feel in your bones, or at least for a few minutes understand, is that this 90% accuracy of the test tells you very little. In fact, it's virtually meaningless unless you know the percent of the population who is infected. If you don't at least make some assumptions about the percent of people who are infected, then the 90% doesn't tell you anything. Think about it like this. If the patient says, look, there's a 90% chance I'm infected, well, they could be wildly inaccurate, because if only 0.000001% of people are infected, then a 90% accurate test is going to indicate that there's a vanishingly small chance that you're actually infected. Whereas if 99% of people are infected, then a 90% chance of a 90% accurate test will say you're almost certainly infected. So without knowing the prevalence, without knowing the frequency of infection in the population, the accuracy of the test plus a positive test doesn't tell you much about whether you're infected. So the person says, so if only 1% of people is infected and the test is 90% accurate, then 8% of people who test positive are infected. 1% is the prior probability you have the virus. It's called the prior probability because it's the probability that you should assign to you having the virus prior to your test result. So prior to your new evidence, the new evidence is the test result. If somebody just asks you, hey, what are the odds you're infected? The idea goes, you might say, 1%, because that's the percent of people in the population who are infected. Now, you need to take account of both this new evidence and the prior probability. So the new evidence is your test result, and the prior probability is the frequency of the infection in the population. You need to take account of both of those things when you decide the probability that you're infected given a positive test. And Bayesian reasoning is a way to do that. The kind of reasoning we just walked through is Bayesian reasoning. It combines the prior probability, in this case the prevalence of the infection in the population, with the new evidence, in this case your positive test result and the accuracy of that test, to tell you what the odds are that you're infected. Now, in this example, the prior probability is the percent of people infected with the virus. That's an objective fact about the world. If the percent of the people infected with the virus is 1%, and you use the percent of people infected as your prior, and I use the percent of people infected as my prior, then we're going to assign the same prior. It doesn't matter who you are, you'll assign the same prior. And that's called an objective prior because what number you should assign doesn't depend on who you are. It's also called informative because it can affect the probability you should assign to you being infected, given that you've tested positive, quite a bit. It could, if almost no one on Earth has the infection, and we test everybody, then the vast majority of people who test positive won't be infected, even if the test is 90% accurate. But if most people have the virus and you test positive, then you probably have the virus, even if the test is only, say, 20% accurate. Okay, here's a question, and it's an important question. What can you do if you don't know the prevalence, if you don't know the percent of people who have the virus? That is, you get a positive test result. Should you infer you have the virus? You don't. You probably do. You probably don't. Well, you need to know the prevalence. But what if you don't know the prevalence? What if you don't know what percent of people have the virus? You can't just use the accuracy of the test. You can't say the test is 90% accurate, so there's a 90% chance I have it if I test positive. Why not? Because remember, the percent of people who test positive, who actually have the virus, is heavily influenced by the prevalence, by the percent of people in the general population who have the virus. Which means testing positive might mean, even if the test is 90% accurate, that you almost certainly do have it or that you almost certainly don't, depending on what the prevalence is. So you need to know that prevalence. You need to know it in order to make sense of your test result. But what if you don't know it? What can you do? You can't just remain neutral. You could remain totally neutral and say, I have no idea what this positive result means. But if you want the positive result to be meaningful, you need to make some assumptions about the prevalence. Well, how can you do that? Perhaps you can use everything else you believe. So, for example, I might say, look, I don't know anybody who has this virus. I've never even heard of this virus, and I know lots of people. So it must not be very prevalent. So I'm going to estimate the prevalence at 1% or less. Whereas you might say, look, I've heard of this virus. In fact, I've studied it. And in fact, I have several friends who have it. So I'm going to estimate the prevalence of this virus at 20%. And what I want you to notice is this. My estimate of the prevalence is based on other things I believe, like I've never met anybody who has it, I've never heard of it. Your estimate of the prevalence is based on things you believe, like you've heard of it, you've studied it, you know people who have it. Assuming those are both, using what I believe to estimate the prevalence is reasonable, and you using what you believe to estimate the prevalence is reasonable, we're going to have different reasonable priors, different reasonable estimates of the prevalence. But those estimates are subjective. They're going to vary from subject to subject because I use what I believe to estimate the prevalence, like I don't know anybody who has it. You use what you believe to estimate the prevalence, like you know lots of people who have it. So the estimate will vary from one subject to another. So it's a subjective prior. This is when you do Bayesian inference this way with subjective priors, it's just called Bayesian inference with subjective priors. Now, there's an objection to Bayesian inference with subjective priors, and the reading goes into all this in a lot more detail. I'm just giving you kind of the overview that you need for examination purposes. If you're interested, I encourage you to look at the reading. Some people say that Bayesian inference with subjective priors has no place in science because science should remain totally objective. Well, remember that perceiving is presuming. And remember that the expectations one brain uses when perceiving are different from the expectations that another brain uses. Why? Well, you and I might put slightly different emphasis on mouth move when deciding what to hear. In the reading, it also talks about experiments on color perception. So if you have constantly associated in your experience Smurfs with the color blue, and someone living in a country where they don't have Smurfs on TV has never associated Smurfs with the color blue, then your subjective prior for that thing is blue given that it's a Smurf is going to be fairly high, whereas their subjective prior that that thing is blue given that it's a Smurf is going to be very low. And insofar as those priors influence what you see, which experiments suggest they do, you'll see the Smurf as bluer than someone who doesn't have that prior. And in fact, you'll see a gray Smurf with just a little bit of blue in it as being blue, whereas that person will see a gray Smurf with just a little bit of blue in it as being gray. There's all sorts of experiments like this. I talk about some of them. Some of them are talked about in the reading. So in this respect, perceiving is subjective. You can also think of this in relation to the experiments we looked at, like the rotating mask illusion. Suppose you stop hanging out with people and spend a lot of time looking at the back of masks. Then your subjective prior for that thing as a face is convex, given that it's a face, is going to be lower than the subjective prior of most people. Consequently, when you see the rotating mask, there will be points where you'll see it as concave and the rest of us will see it as convex. In the McGurk effect, if you stop investigating, if you stop watching people talk and you close your eyes whenever anybody talks, gradually the association between mouth movements and sounds produced will break down in your brain, and you'll be less subject to the McGurk effect. Your subjective prior for that sound is far, given that the person is mouthing far, will be different than mine. Now, science, of course, must use perceiving, so you can't object to Bayesian inference with subjective priors just on the grounds that it would be introducing something subjective into science. There's already something subjective in science, and that's perception. So here's a question. Does the fact that both perceiving and reasoning, specifically Bayesian inference with subjective priors, rely on subjective priors imply that they can't reveal objective truth? So does the fact that perceiving and reasoning rely on subjective priors suggest that we're sort of all living in our own worlds and there is no objective truth, or at least we can't know objective truth? The answer is no. And I'll give you a very simple example to show that it doesn't imply this. Now, it may be that we're all living in our own worlds and that there is no objective truth. That's possible. This isn't an argument that that's false. Instead, this is an argument that goes as follows. The fact that reasoning and perceiving are subjective does not show or even provide evidence for the conclusion that we can't know objective truth and that reasoning and perceiving don't lead to a knowledge of objective truth. So why not? Well, imagine you're standing next to me as we gaze at a painting, say Vincent van Gogh's Starry Night. Even though we see the painting from different angles, you're a couple feet to the right of me, say, we learn about the painting itself, not just a point of view. I learn that the painting includes yellow and blue, not just that it includes yellow and blue when you look at it from this position, right? It includes yellow and blue from my position, it includes yellow and blue from your position. So I'm not learning, and it's rectangular from my position, it's rectangular from your position. I'm not just learning about the properties the painting has when you stand here, I'm learning about properties the painting has. And the same goes for you. You're not just learning about properties the painting has when you stand there, you're learning about properties the painting has. Now, we can both learn that it has lots of blue, some yellow, and some white. We can both learn that it depicts houses and so on and so forth, despite the fact that we have different points of view because we're standing in different spots. And that it has some yellow, some blue, and some white, and it depicts houses and so on, are facts about the painting itself, not facts about a point of view. Perceiving can teach you about the painting, even though you always perceive from a point of view. You have to be standing somewhere or sitting somewhere in order to look at it, or more generally located somewhere. The fact that the point of view includes your brain's unique set of biases, not just the angle between you and the painting, doesn't change anything. It's still the case that you can learn about objective features of the painting from your point of view, even though your point of view doesn't just include your location, but also includes the subjective priors which influence how you interpret how your brain interprets incoming signals and influences how your perceptual experiences are produced. And the same goes for reasoning. Reasoning from your background beliefs can tell you about the world itself, even though others have different background beliefs. Now, when my background beliefs lead me to a different conclusion than your background beliefs lead you to, one of us is going to be wrong. At least one of us, maybe we're both wrong, but at least one of us is going to be wrong. If you think, your background beliefs lead you to conclude that you almost certainly don't have the virus, and my background beliefs lead me to conclude that you almost certainly do have the virus, one of us is getting it wrong. It may be hard to say which one, But presuming that your background beliefs, say, are better than mine, it turns out that your probability assignment is the correct one and mine is the incorrect one, then your conclusion is justified and my conclusion is in some sense unjustified. Okay, that's all I'm going to say about this. Again, there's a lot more about this in the reading if you're interested in thinking about it further.